Okay, so for this first part, you just need to set up a system of equations, one that describes the movement of the center of mass and one that describes the rotation. So for the center of mass, the only two forces acting on the center of mass are the force of gravity, which is mg sine theta, which you can figure out from this, and then the force of friction, which causes the rotation. And we know that that's going to equal mass times acceleration. So now we know everything. All these are constants except for the force of friction. So what we do is we isolate the force of friction. So we say mg sine theta minus ma equals force of friction. So now we need to find the force of friction. So that's where we use this equation here. So we know that this gives us our net torque, and this gives us our angular acceleration. Sorry, this angular acceleration, this is moment of inertia. So we get net torque equals I times angular acceleration. So that's how we get that. And then angular acceleration is the same thing as a over r. And then what ends up happening is this one r cancels here and the other r cancels there. So then you're left with force of friction equals ma, which is right there. And then you plug that back into your original equation, you get here. And then you can find that mg sine theta is 2ma. And then if you just solve for a, you get g sine theta over 2 equals a. Okay, so now for the speed of center of mass, what I didn't really feel like doing kinematics, so I just used energy. So the initial energy, and if we're just including this part, we don't really care how high it is above the table. That doesn't really matter. Gives us mg L sine theta, right? L sine theta is just this part. L here, sine, opposite over hypotenuse. So this is mlg sine theta, which equals the translational speed, 1/2 mv squared, plus the angular speed, 1/2 angular momentum times w, which is just v over r squared. So now this, and what ends up happening is this r squared and this r squared cancel out, and you're just left with 1 m over v. All the m's cancel out, so you're left with g sine theta equals v squared. So then the square root of g L sine theta equals v. So now for the horizontal distance from the edge of the table to where the hoop lands on the floor, what we basically have to do is we have to solve a kinematic equation. So we know the speed of the center of mass, which is right here. So what we can do is we can set up a kinematics equation in the y direction. We know that the displacement in the y direction is h. We're trying to find time. We know that g is a, v naught is 0, and we know v final is gl sine theta, right? But we actually don't need g final. G final is actually horizontal, so it doesn't apply to this scenario. So then we're able to get that h, which is the same thing as delta y, equals 1/2 gt squared. So that means 2h over g square root equals t. So now we know that velocity in the x direction times time equals delta x. We just got time here. We have velocity in the x direction here because it's the velocity of the center of mass. So we multiply these together to get 2hl sine theta root. Now, final question, same mass, same radius. How will the distance change if it's a disk versus a hoop? If it's in this case, it's a hoop, so all of the mass is really far away. If it's a disk, the mass is going to be spread more evenly, which means it's going to have a lower moment of inertia. Now, we don't have moment of inertia in any of the final equations just because everything canceled out really nice. But this mr squared represents the moment of inertia. So if this decreases, right, nothing else here is changing, right? This stays the same. This is going to stay the same. So, then the mass doesn't change at all, right? The only thing that's changing is the moment of inertia. So if this gets smaller, the only things that can increase are the velocities. So if velocity is increasing, right, velocity increases, so this GL sine theta increases, that means that our delta x is also going to increase. So the distance measured is going to be greater than